All right, so now you've given it some thought. Well, given the techniques that we've covered so far, here's one thing you may have thought of. Namely, why not take every pair of populations and test each one of them out as a two-sample problem. So for example, you might say mu1 minus mu2 equals 0, and then do a mu1 minus mu3 equals 0, or a mu2 minus mu3 equals 0, and test all of these. Test all of these hypotheses. Well, yes, you could certainly do that, but think a little bit. What would happen to your error rate if you did that? So for example, if k is equal to 5, then you would have 5 combination 2, so that's 5 items taken 2 at a time, that's equal to 10. So you would have to test 10 hypotheses if you did them in a pairwise fashion like that. Now, what's the probability? Even if each one of these hypotheses were correct, or if the initial one, the main one, that mu1 equals mu2 equals mu3 equals mu4, even if that hypothesis is correct, what's the probability that you will make the right decision 10 times? If you do it once, let's say you've set your alpha at 0.05, then 1 minus alpha would be 0.95. So you would have your probability is 0.95 of not rejecting the null hypothesis when you shouldn't be. What about doing it 10 times? Well, it all depends how dependent these 10 tests are, but if they were independent of each other, then the correct answer is 0.95 to the 10. And look at what happens to 0.95 when you multiply it by itself a number of times. In other words, this 95% chance that you had when you did just the one test has now gone down to 60%. So it's not the best approach to take. It is the one that people thought of at first, and so it's the sort of thing that's very natural to do. Alternatively, what we can do is something called the analysis of variance. We are going to look at the variance. Even though we're interested in the means, we're going to look at the variance. And actually, it's very, very ingenious. But what we're going to do is we're going to look at how different estimates of the variance compare. And if the null hypothesis is true, we expect one thing to happen. And if it doesn't happen, then we'll say, oh, wait a minute, maybe I don't like the null hypothesis. So let's start. Now, we have the assumption of homoscedasticity. So our assumption of homoscedasticity tells us that each one of these variances or standard deviations in each of the k populations, they all measure the same thing. They're all measuring a common value, call it sigma. They're all trying to estimate the same sigma that's common to all of them. So why don't we just combine all these, combine them together, and form what we call the within estimate of the overall variance. So it's just looking within each one of these k samples, give me an estimate of the variance. And then I'll combine them, but I'll do a weighted one, because if some ends are small and some ends are large, I want to give more weight to the large ones than to the smaller ones. But that doesn't matter. So we'll just combine them all. So this is what is called the within variance estimator. And for this to make sense, we just need that the homoscedasticity assumption is correct. Okay, so that's one estimator we can have of the variance, of this common variance sigma squared. If the null hypothesis is true, then what do we expect to see? And we'll start progressing that way. So if the null hypothesis is true, we expect all the means to be equal. That's what the null hypothesis is. Now, let's look at these k groups. It's as if we were sampling k times from the same population. Remember, it's a normal population. They all have the same standard deviation. They all have the same means. So these k samples can be considered as sampling k times from the same population. Okay, so here they are. Here are my k samples. Under the null hypothesis, I'm sampling from the same population. They're different sample sizes, okay, but the null hypothesis is that I'm sampling from the same population. All right, so let me get rid of those. So what do we have here? Well, each one of these is estimating the same quantity mu. Also, each one of these is estimating the same quantity sigma. So what I can think of all of this is that this is one sample from a population with standard deviation sigma. Here's another one, and dot 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 dot. Here are another one. So I can think of these k as k different samples. So these are my k samples, all from the same population. I have to be a little bit careful about the sample sizes, but apart from that, they're all from the same population. So what I can do from the central limit theorem, this one, the first one, is from a population with standard deviation sigma over the square root of n1. This one is from a population with standard deviation sigma over the square root of n2. But both of them are going to give me information about sigma. In fact, all k of them will. So why not combine all of them together and come up with an overall estimate of the variance? So what we can do is, first of all, we'll get an overall estimate of the mean, because they're all estimating the same mean. Once again, I want to do something that's weighted because I want to give more weight to the larger samples, etc. But that's the same as just ignoring what sample they belong to, and just taking all the x's, summing them all up, and then just dividing by n, where n is the total sample size. Okay, so now I've got that. Now, each one of these, like x1, also is trying to estimate mu. Now I can take the estimate of the variance, acting as if these x bars were my, that should be a k, acting as if these x bars were my observations. Here is another estimator, or another estimate I should say, of the variance. We'll call this the between estimator. It's gotten by comparing the x bars. And the genius of this all now is just to compare those two. To compare the between and the within, we call them sums of squares. So compare the between and the within estimators of the variance. Mean squared error, actually. Because if the null hypothesis is true, if the null hypothesis is true, then this should be approximately 1, and so if we get this close to 1, then we would say, the data are consonant with the null hypothesis. If this is bigger than 1, say, then we might reject the null hypothesis. So just like we had the z and then we had the t, now we've got what is called Snedeker's f. Snedeker dedicated this to Fisher, who was in the 20s, wrote one of the most important papers about this analysis of variance.